Today we're talking about Lewis diagrams, and I'm going to guess that at some point you have drawn structures that were meant to look like molecules based on counting valence electrons and then connecting the dots. We're going to do things a little bit differently because what you used to do, or when you learned it that way, it worked for a select few group or a select group of molecules. It doesn't work for everything. We want something that works for a much larger group of molecules. So we're going to start out with identifying what the problem is. If I asked you to draw a Lewis diagram for sulfur dioxide and you were counting up the valence electrons and starting with drawing the valence electrons, you would say that sulfur has 6 electrons, valence electrons, and oxygen also has 6 valence electrons. If you were to arrange those valence electrons around each atom and then identify where you're going to form the bonds, where the single electrons are, the first bit is actually pretty easy, but then I end up with these single electrons on oxygen. And those become the problem. Now, the obvious solution to the problem is to connect those dots. The problem is the Lewis diagram is meant to look like the actual molecule, and the actual molecule looks nothing like that. So that is absolutely wrong. So what we need to do is revise our way of doing Lewis diagrams so that we do a much better job of drawing molecules. Also, some structures that we're going to draw actually have ionic charges, and what do we do with that, right? Where do we put those electrons? So what we're going to do is we're going to go through these steps. It's going to feel a little bit longer, but it's also going to be much more reliable. It's going to work for practically everything. You're going to still start out with counting all the valence electrons. You're not going to start by drawing those valence electrons, but you're definitely going to start by counting the valence electrons. If you have an anion, that is a negative ion, you're going to add the correct number of electrons. If it's a cation, a positive ion, you're going to subtract those electrons. You're going to arrange the outer atoms around the central atom. Now we'll talk later on about how do we pick which one is going to be the central atom. Then you're going to connect the central atom to those outer atoms with a bond. Single bond, that's going to represent 2 electrons. Then you're going to complete the octets of the outer atoms. There's a little couple caveats that we're going to have to take care of in a moment, but generally speaking, you're going to complete the octets of those outer atoms. If you have leftover electrons, you're going to add those to the central atom in pairs, always pairs. Same thing with the previous one. Now at that point, you might go over an octet for some atoms, and that's okay. But you also might be under an octet. That's a problem. If you are under an octet on the central atom, then you're going to do this. You're going to add double bonds. And all that means is you're going to take electrons that you had on the outer atom and you're going to move those into a bonding position. Okay, how do we count valence electrons? You probably know this, but let's remind you. It comes down to the periodic table, which is probably one of our most useful tools. We're really only dealing with the nonmetals here in the tall columns, where let's say start with column 14. Column 14, 1, 4, 4 valence electrons. Column 15, 1, 5, 5 valence electrons. Column 16, 1, 6, you guessed it, 6 valence electrons. And it continues on all the way over to column 18, 1, 8, with 8 valence electrons. Check, done. Okay, so I'm going to get you to write these down. I'm going to get you to pause the video. I'm going to get you to count up the valence electrons, and then we'll come back in a moment and check on your work. Okay, you should have paused. Maybe you did, maybe you didn't. You should have. But the number of valence electrons you get should look like this. So 26 for the ion, SO3 with a 2 minus charge, and you can continue reading those valence electrons, double checking your work. Okay, so now we know how to do the valence electrons, and again, if you have an ion, you either add electrons for a negative ion or you subtract electrons for a positive ion. Okay, central atom, how do I know that? There's a few things, and it's never going to be like one particular rule all the time. We sometimes take a balance between a few rules and see which one makes the most sense. It is sometimes the first atom that's written in the formula. Often, actually, except it's hydrogen, it's never going to be hydrogen as a central atom. Often there's only one of that type. Okay, if you look back at the ones we've had so far, it's often been one sulfur with 3 oxygens, or one phosphorus with a few other things. It's often the one that's least electronegative, which means on the periodic table, it's often the one that's further to the left. Not always, but often. Except hydrogen. Hydrogen is way over on the left. It can also be I guess that was it then. If I give you these examples, and again, same examples you had before, so you already have them written down, take a pause and see which one you think is going to be the central atom. And then we'll unpause it, and then we'll find out if you're right. These would be the central atoms. Now you'll notice that in the last one, xenon is definitely not farthest to the left, but it is only one. It is written first, and it is the least electronegative of that group. So, okay, get into drawing Lewis diagrams. I'm going to draw the Lewis diagram for sulfur tetrafluoride. Now what that means is I'm going to start by counting all my valence electrons. I'm going to be going through those steps. So sulfur has 6 valence electrons, fluorine has 7 valence electrons each. There are 4 of them, gives me a total of 34 valence electrons that I have to account for. I'm going to start by arranging the outer atoms around the central atom. Based on what I've done before, it's going to look something like this. Notice there's no valence electrons there. All I've done is arrange my atoms. I am then going to attach the outer atoms to the central atom using electrons in bonds. I'm going to draw the line. That single line represents 2 electrons. So if I count that up right now, I've accounted for 8 valence electrons in my diagram. Then I'm going to complete the octets of those outer atoms, the fluorine atoms. Well, they all have 2 electrons on them right now, so I'm going to put 6 more in pairs. So now I've got complete octets around my outer atoms. If I do a count now, I've got 32 electrons, and right now everything looks pretty good. Everybody's got an octet. Everybody should be happy. The outer atoms have an octet, the inner atom, the central atom has an octet, but I only have 32 electrons, not 34. So what do? My next step is to add remaining electrons in pairs to the central atom. So I do that. Now sulfur right now has more than an octet, but that's okay. I have to get those 34 electrons. Now my diagram's complete. Well, how do I know when to do that? Follow the steps. Well, what if it breaks the octet rule? It did. That's okay. What if I don't have an octet? Well, in this case I don't have to worry about it, so let's do one where I do. Sulfur dioxide. Hello darkness, my old friend. That's the one that we started with, saying we needed a new way of doing Lewis diagrams because the old way just did not work. Does it work for this one? Well, I hope so. So I'm going to do exactly the same thing. Count my valence electrons. I'm going to arrange them around the central atom. I'm going to, let's go back to that one. Arrange them around the central atom. Sulfur makes the best central atom. I'm going to connect the outer atoms to the inner atom, 2 electrons. I'm going to count my electrons. I'm going to complete the octets of the outer atoms. So now I'm up to here where my oxygen has stable octets, but my sulfur does not. 16 electrons. I've got more to go. I can add remaining electrons to the central atom. Now all the electrons are there, but if you look, sulfur does not have a stable octet. Last time it went over a stable octet, now it's under a stable octet. Over is okay, under, not okay. So I'm going to fix that by moving non-bonding electrons from one of the oxygens into a bonding position so that oxygen still has a stable octet on both sides. Sulfur now has a stable octet. How do I know which one to move? And that takes a little bit of experience. In this case, they're both oxygens, so it wouldn't really matter. Some cases, there would be an oxygen and a chlorine, for example. We'll talk about that. Oxygen is always a good option if it's one of your options. I'm going to leave you with some to try. I'm going to get you to write these down. If you follow the steps, steps will start to make a lot of sense. You won't have to go back and check all the time. 2, you get really good at Lewis diagrams. So please practice these. Okay, at the end of the day, a couple things we've learned. Number 1, we've learned how to count valence electrons, which actually takes a little bit more effort than you think. We've learned how to select the appropriate central atom. At least that's going to take some bit more practice, but we've got the basic idea. And then we can draw actual Lewis diagrams that should look a lot like how the molecules actually look. And then we'll talk to you another time. See you then.